Okay, so today we are actually going to talk about greedy algorithms. So greedy algorithm is a very important strategy of design algorithms. So intuition is also actually quite intuitive. So in general, so when we want to talk about like for solving a problem, so you can see that basically by greedy is just like a natural move is that we want to select the best possible option at the current moment. A natural move is to choose best option at the moment. So this is just like a very a standard like intuition here. Or in other words, this is typically called like a short-sighted greedy. So you can imagine that basically for such kind of short-sighted greedy, sometimes it's probably going to fail. Maybe you should have like a more long-sighted kind of algorithm to solve the problem. But today we are actually going to talk about some basic algorithm that basically are using some short-sighted idea you can do pretty well in general. So, but in general, I think we talk about like short-sighted greedy or maybe long-sighted. This is in general quite hard to formulate this. I mean, rigorously. So I would say that it's hard to find rigorously, but a natural strategy in algorithm design. So talking about the greedy strategy in general, we can talk about quite a few different kinds of algorithm. And I think basically for the first two classes, I think especially for the last class, we talk a lot of properties and algorithm and graphs. So I think we are for when we want to talk about greedy algorithm, we are also going to start with graph problems. So the first problem that we are going to take a close look today, let me actually add a new page here. So the first problem that we are actually going to study today is the shortest path problem. So for the shortest path problem, we are going to have a directed graph. G equals to VE. So we want to talk about the path on graph. So here we actually have like a source, or maybe you want to call this like a starting point. S, and also a destination, or maybe called like a terminal. T. So there are actually some lengths on the edges of the graph. So length is LE equals to the length of edge E. And we assume that the length of all the edges are non-negative. So this is maybe actually a little bit abstract, but maybe let's see a specific example. So we are talking about directed graph. So maybe let's draw something like this. So here is like the starting point S, and maybe finally we have a point T like this. So there are some edges between this, like in general among this graph. So maybe let's assume that has like a few vertices. For instance, like we have 1, we have 2. Let's say we have 3 and 4 here. So in general, maybe let's consider, for instance, like this directed graph. Yeah, so this is just like a example of a directed graph. And because we are talking about like lengths of the edges, so this is in general like a weighted directed graph that we have weights on the edges. So for instance, maybe let's consider this. Maybe like I'm just like writing down some numbers on this on these edges to represent corresponding lengths. So assume like maybe for instance this 7, this is 8, this is 10, and this is maybe like 6, 5. Or maybe, for instance, like this is 9 here. Yes. So for this graph, we can talk about different paths from S to T. You see, like there is not like a unique path. There are actually a few different paths that can reach from S to T. So for instance, maybe let's consider this. Maybe we can consider like the path where we want to from S to 1, from 1 to 3, and from 3 to T. So what is the cost of this path? So I guess this is relatively straightforward. You just combine them together. It's like 3 plus 10 plus 6, which is 19. On the other hand, we can also consider some other paths. So for instance, maybe we can consider like from S to 1, from 1 to 4, and from 4 to T. So this is going to give you the weight like 3 plus 8 plus 5, and this is going to be 16. So you see, like basically we want to talk about the shortest path. So in this kind of sense, I guess this path like a 3 to 1, 1 to 4, 4 to T is probably better than the path like 3 to 1, 1 to 3, 3 to T. So this is basically in general the shortest path problem that we want to solve, and let's actually formulate this. So the shortest path problem is to find the shortest path. I think we should emphasize that because we are actually working on directed graph, so we are actually finding the shortest directed path. From S to T. So basically by the shortest path, or basically in general want to talk about this as short or long, you need to really talk about the length of the path. So in general, we make a remark that the cost of path is basically sum of edges, basically sum of edge costs, sorry, in path. So any question of this problem definition? Shortest path problem. Okay, so I guess this is relatively easy to understand. So let's, in general, maybe before I give you an answer, maybe you can think for a few minutes that if you want to solve this kind of shortest path problem, I mean, and also I tell you that like a greedy strategy might actually work well. So what is the specific kind of greedy strategy that you're going to use here? I mean, it's like in general, maybe you want to do basically want to solve the problem in a greedy sense, but greedy of what? So in general, we are talking about shortest path, but in general, maybe you want to think about how you can actually construct a corresponding path, maybe for instance, in a greedy way, or in general, how you're actually going to do this. So maybe let's actually stop for like 1 to 2 minutes and you can think a little bit more about this. Yes, yes, yes. Or in general, I mean, I'm talking about like in the shortest directed path, just like means to find. Or maybe let me yeah, so maybe let's talk about how we are actually going to do this. So we think about like, for instance, like a greedy strategy, but you cannot like suddenly, I mean, this is in general like a large graph. It's not very easy that you can figure out like a shortest path from S to T, but maybe you can do this gradually. I mean, the greedy in this kind of sense is that we gradually compute like a set. Maybe maybe we cannot at the beginning solve like shortest path problem from S to T. But for instance, here you can easily see that like the shortest path from S to 1 is just like the edge from S to 1 because this is just you can do this of course basically the cost of 3 from S to 1. So basically, the strategy is that you can consider like a certain set S, maybe for instance, and in general, you want to like increase the size of the set S such that at one time you have like a good maintenance that basically inside a certain set, you always find like the shortest path. And in general, you can make this larger and larger. And finally, you want to make sure that this contains like, for instance, all the vertices. And this is also going to contain the vertex, a T here that finally you're actually going to be interested in. So this kind of strategy that you use like a greedy strategy and you want to gradually compute like a larger and larger set such that the shortest path from S to the corresponding set in this vertex set is correct. Basically, this strategy is called the Dijkstra's algorithm. Dijkstra's algorithm. So let's actually formulate everything and actually make this more formal. So this is basically by doing like this. So we maintain a set of explored nodes S for which we have determined so we use D of U to denote, we use D of U to denote the shortest path. I think I should, English is going to be a little weird. So it's the distance of the shortest path. Oh, sorry. From S to U. So basically want to maintain such kind of set. So the algorithm is that we initialize. So of course, at the beginning, we don't know like anything else, but we know that initially we can initialize the set S to be just contain the starting point, the small s. And of course, the distance of S is just going to be 0. So while, maybe let me use the red color here. So while this S, I mean, has not been the whole set. I mean, there are still vertices that we haven't figured out the shortest path. We can do such kind of things. So we basically find a V belongs to V over S because we haven't found all the vertices. So there must be a point that we have not figured out like the shortest path from S to the corresponding point, which we denote as the vertex V here with at least one edge from S that minimizes this. So minimize, we call this like a pi V to be the mean of the edges V such that U belongs to S. So let's take a second look of this line. So maybe let me actually write things more clearly. So we want to find a V belongs to V over S, that basically the set of vertices that we have not determined the shortest path. We consider all such kind of vertices V, and we find like the one such that can minimize this value. So basically this value. So what is this value? So in general, we consider the case where we have like an edge UV, that basically we have figured out the shortest path from S to U, that basically we see here that basically the U here is in S. So basically we have figured out, we consider this kind of mean where this a U is taken from the vertices on where we have figured out the shortest path. And the V here hasn't. I mean, basically we consider such kind of case, maybe for instance, let's assume like currently this is the set S that we have figured out. So basically we just consider all such kind of edges. So maybe here we have a U here and here we have a V here. And we consider all such kind of edges. So we take the minimum among all the possible such kind of U and V pairs. So basically here we are taking the U belongs to S, and also the V here is the V over S. We consider all such kind of possible choices. And here, because U is already in S, so basically we here we use the DU here, this D notation here. So we have figured out the shortest path. Maybe for instance, this is S. We have to figure out this. We find the minimum among this, and basically we define this. We consider like this path, and this is like a V that we figure out this time. And after figure out this time, and I think it is apparent what we are going to do next is to actually add V to S and set E of V to be pi. So basically this greedy strategy is that each time we are actually relatively conservative, that each time we increase the set S by one vertex. And the way that we increase this is actually using a greedy strategy that we can consider all like the shortest paths that we have figured out, and basically an edge that can actually extend this. So basically U is in S and actually V is in V over S. And basically we consider minimum among this and we add this corresponding V to the set S. And we are going to do this recursively until that the set S here is the whole vertex set. So is this algorithm statement clear to you? So any question about like the formulation or the motivation here?
So it's the new division. So for example, the step is the minimum, but at the end it leads to a more cost than choosing another. It just greedily chooses one.
Yes, yes. So each time it chooses greedily one at a time. So I guess you are worrying about like the time cost of this algorithm.
Yes.
Yes, I will talk about like the time cost of the algorithm. Yeah, I think for now, I just want to make sure that all of you understand like the algorithm description in general, what is being greedy inside this algorithm. Okay, so if there is no question, I think let's get deeper into this Dijkstra's algorithm. So we want to talk about, we want to make sure that this algorithm is correct. And basically from one of the students' question, we also want to make sure that this algorithm is efficient, that we have good control of the running time of this algorithm. So I think the first thing is that we want to talk about something meaningful. So let's first establish the correctness of this. So let's write this as actually as a theorem. Let's actually phrase it so. Enter this. So a theorem. So for each node, U belongs to S. PU is actually this is correct according to the definition. So it is the length of the shortest SU path. So we prove this. So for this proof, you can see that basically we use the greedy strategy that each time we increase the set S by one vertex. So it also makes sense that we are actually going to prove this by induction. And let's say that we prove by induction on the cardinality of S. So basically at the beginning, so S equals to 1. This is actually relatively straightforward because added V satisfies pi V equals to mean of so this is just by the definition because here, so let's recall here. So here for the definition of pi V here. So here we're talking about the address where U is belongs to S and V is belongs to V over S. But at the very beginning, the only vertex that belongs to S is S per se. So here you see that this is the reason why we read the S here. And basically we are talking about like the V here, because in general, if you want to talk about the edge set, and edge set here, of course, V is going to be different from S, and actually V is of course going to be in S over, V over S here. So in general, this makes sense. And basically what we return here It's just like the pi v according to the definition of the algorithm. Yes. So let's continue. So all other paths contain an edge from S have length larger than pi v. So this is a relative straightforward because we consider assume that we have a set S here, and this v is taken from this minimum definition. So because here we know that SV is actually an edge, so we have this edge. So assume that this dv is not actually the minimum, but maybe you have some actually another path. For instance, let's consider some other paths that can reach v. They actually maybe have like even smaller like the path length. But this is actually you look at, for instance, like the first vertex. So why look at the first vertex on this path denoted v prime. Because due to the definition of this pi v, we are really choosing the edge that with the minimum length along this. We actually already have the length, basically this cost of S to v prime. This is already larger than the cost from S to v, and this is d. So needless to mention that in general, you consider all these kind of paths and just like look at the first vertex along this path. Then due to like the greedy property of this v here, you are really choosing the minimum weight here. Basically, you look at the first, you actually look at this edge. This edge is already more expensive than this, and you don't even need to look at other edges. So that basically gives you the promise at the very beginning, the algorithm works correctly, that you got the shortest path from S to V at the very beginning when you move like from the cardinality of S from 1 to 2. So any question for this beginning step? Is this clear? Okay, so I guess this the very beginning step should be always the easiest thing that we can consider. So let's now assume the correctness. Or let's say the cardinality of S equals to K, which is larger than 1. So that we, the node, added to S by the Dijkstra's algorithm. And let's also let's make the notations here to be clear. So let's denote UV should be the chosen edge. So let's actually also draw a graph here. So to assume that currently this is our set S. Our set S. And assume that the beginning at the beginning we have a starting point S here. So here assume that this is the UV edge. So the U here by definition it is inside this set S, and we have a V here. Basically we have this this edge. So I think we have basically figured out like an edge is set here, and actually on this edge this path, sorry, a path from S to U, and basically we figure out the path that with the shortest path with the corresponding cost du here. And by the assumption in the induction, this is correct, that this is actually the shortest path. So this is the notation that we use. So we consider next. So the shortest path shortest path between S and U plus edge UV is an SV path of length pi v. This is just due to the definition of the Dijkstra's algorithm, that basically the output that we got from this equation star here is this UV edge, and basically the corresponding cause is pi v here. So we want to make sure that this pi v is actually equals to dv, which is the shortest path from S to V. So that's in general, to prove this, we consider any as V path in here. So we just in general want to make sure that this path, this path we have drawn on this figure that from S to U and U to V is actually the shortest path. But to prove this, we consider some arbitrarily other paths P here. So maybe let's assume that XY is the first edge. In P that leaves S. So in general, we consider, because we are talking about some other path. We consider like from S to V here. Maybe there are some other paths, but let's actually look this in a closer sense. So the first edge that leaves this, from X to Y, let's just like actually grab this. And maybe there's also like here, because also we know that this S is inside the vertex set S here. So we know that it is actually good inside this set S here, that we know this dx. But after that, leaving this set S for the first time, we want to make this precise, and we consider this where actually this edge xy is the first time it leaves the set S here. So we have this edge and from X to Y, and maybe later on it says can return the set S here. This is not a big problem. But in general, we just draw the path like this, and we take a very close look at this xy, the first edge in P that leaves S. So let's take a very close look at this and see what is actually going to happen. So let P prime be the subpath to X. Or basically, this is the P prime. So the observation is this. So P is already too long as soon as so basically, in some sense, we are actually trying to grab something similar to this very basic discussion. That maybe if you want to consider something else, maybe you want to figure out another path, but maybe this path is actually not so helpful, and maybe at a certain place it is already too long. So we take a very close look at this edge, from X to Y, is that basically we can consider such kind of observation that L P. So this is basically the length of a path P. So of course, this is going to be larger than L P prime plus the length from X to Y. So this is basically maybe this is like a whole path. You have this part, you have this part, and you have this part. But actually, we are actually only talking about the first two parts. We talk about S to X and then X to Y. We just like look at this part. We don't want to like even further look at from Y to V here. And actually, we can already get some contradiction, or maybe we can already show the thing that we want to show here. So I guess this is relatively straightforward, or maybe let me even give some annotation here. So this is basically like ignore the part from Y to V. And also, very importantly, we should emphasize again that the weight or the length of all the paths is actually non-negative. So that's why we can ignore this. Or maybe if this is not an assumption, if you ignore a part where the path length is negative, then this is definitely not okay. But here we want to make sure that we have the assumption that all the weight is non-negative. So that is a reason why we can simply ignore the part from Y to V. Actually, maybe let me, this is the vertex V here. If it looks too similar to you here, just be careful. Okay, so we got the first inequality that the length of P is actually larger than or equal to the length of P prime plus the length from X to Y. So the next thing we know that is actually this is actually larger than dx plus. So this is just for like a sanity check. I mean, in general, you want to talk about a path. I mean, a p prime that the first time it leaves is at the vertex x here. But maybe you are not clever enough and you're not using the shortest path. But in general, it is of course it's going to be true that you can consider like a path from s to x. And actually, this x is already in this vertex at s here. So you know that we have the value of dx in hand, and actually we have this, and this is just like by the fact that x is already in S. So any question up to this point? Okay, so I think the next inequality is then relatively easy to see because the main reason that we actually want to focus on this edge, I mean this edge from x to y, the first time that leaves the set S here, is that we want to make a direct comparison to what we are using here in the greedy strategy. So basically this equation, a star here. So because we are actually taking the minimum, I mean, in this definition, we want to consider minimum of like a du plus Le, where basically this the E here is the edge is like a UV edge. I mean, U is in S and actually V is not in S. But we exactly see that actually the edge XY here also satisfies this definition. I mean, X is in S, but Y is not in S. It's actually in V over S. So this is by the definition, and this is just like due to the greedy part. We know that dx plus L on xy is actually larger than pi y. Oh, sorry, I think I'm not saying it correctly. And actually, I should say that this is larger than pi. I think the greedy is this. Sorry. Greedy is this. And actually, this is larger than pi y. This is also relatively straightforward. This is just the definition of pi y. So here the pi y here, I mean the pi definition is basically defined as this. It's actually defined as the minimum that you can take from this. So this kind of a path, I mean the edge x to y, this is definitely a path that satisfies the definition inside this pi one. I mean basically the right hand side of this equation star here. So that is the reason why I think this you can see that dx plus Lxy is larger than pi y. I think what we were actually just talking about, like the greedy part, is actually the last inequality. But due to the strategy, greedy strategy, that basically this y actually satisfies the definition in the greedy part. So that is actually from this you can see pi y is larger than pi b. So this basically, by using this chain of inequalities, you can probably have seen that we have basically established this, that T is already too long as soon as it leaves S here. So this basically finish the proof of Dijkstra's algorithm. So any questions? Is this proof clear to you? Any online questions? Okay, so after having the correctness of Dijkstra's algorithm, I think the next thing that we need to talk about, I think also one of the students asked the question that in general, I mean, how about the running time? I mean, whether this is like an efficient algorithm. I think this is definitely something we want to have a better understand. So running time. Dijkstra's algorithm. So we make the following observations. So the Dijkstra's algorithm has n-1 iterations of the while loop. So this is basically because each time we only add one vertex. At the beginning, we have one vertex, the vertex S, and finally I mean, the whole set is n vertices. So that is basically the reason why there are n-1 iterations. So we have n-1 iterations of the while loop for a graph with equals to n. So in each iteration, so we want to be careful about what we do in each iteration. We need to add a v. And actually this requires like we need to go through this. The mean of the E of UV where the U is in S, and actually this edge is belongs to E. So basically we need to go through all such kind of edges. I mean, all these edges that basically the U part is in S, and actually it is an edge. So we need to really go through this. In general, in the worst case, I mean, you just look at this S. Just look at this S. In general, there can be a lot of edges, I mean, right between S and like V over S. So in general, this is something we really want to be careful. And in general, you can see that in the worst case, we need to go through, roughly speaking, like a linear in M edges, or close to all the edges. So this is like O of M cost. So we have n-1 iterations, and in each iteration, in the worst case, the cost is O of M. So that is basically saying that in total, the Dijkstra's algorithm runs in O of Mn time. Is this clear to you? So do you have any question about this? Yeah, but actually, I mean, of course, correct, as I think this is relatively direct. You can see that the Dijkstra's algorithm runs in O of Mn time, but maybe you are not totally satisfactory with this answer. And I think actually during the discussion that we just made with one of the students, and actually this is probably not like the best thing that we can observe, that each time we are like we check all the edges. I mean, basically we need to check the edges in this greedy strategy, that we check all the edges. I mean, like U is in S and V is in V over S, that basically we check this. So this sounds quite repetitive, actually. I mean, maybe for instance, like some edges you in different iterations, you actually check those for like again and again. So this is really not the situation that we want. And I think a very natural question is that whether we can improve the running time of the Dijkstra's algorithm. So maybe let's write this down. I mean, or I think maybe we can say that the computation of pi v can be, let's actually even highlight this, can be very repetitive. So this needs actually more advanced, but more advanced of what? So basically here we need a strategy that we can have a better way to store all these kind of values. Basically this value in this star here. So basically we need some better strategy that we can store this value such that we don't have to, I mean, start over each time. I mean, and hopefully like this kind of minimum is for some edges, it's not checked for many times. So we need a better strategy to maintain this. And I think to maintain, or basically we have a good maintenance of these values. This is really called some advanced like data structure. To store these values. So let's talk about how we can actually do this. So this comes to a very important conception in basic data structure, and this is called the priority queues. So here, let's actually leave the problem of the shortest path, basically this Dijkstra's algorithm for a while, and let's in general talk about how we can maintain some certain kind of data structure that we are interested in. So let's talk about something that in general we need to maintain a dynamically changing set S. So here, for this Dijkstra's algorithm, or maybe in general, as we are actually going to discuss, that for a priority queues, we want to have such kind of general data structure that can solve like dynamical problems. Here, so for the Dijkstra's algorithm, you can see that actually we are updating this as, and actually this corresponding values, this pi v in a dynamical sense. So that is why we are saying here, in general, from a high-level perspective, we are actually going to maintain like a dynamically changing set S here. And also on the other hand, it is very important that we have values that basically we have value of this kind of shortest path. I mean, we want to actually maintain throughout. So we say that each element V belongs to S has an associated value KV that denotes, let's say, like the priority of element V. So because we are talking about like minimum problem, or in general, in some cases you can talk about like the maximum of such kind of problem. But here it is in general symmetric, and here we are talking about the smaller cases. That in general, we say that smaller keys represent higher priorities. So this is in general from a rough perspective that we want to study such kind of so-called priority queues. Or this is actually still a little bit too rough, and I think we want to be a little bit more, even more specific about like what is the specific data structure that we are actually going to maintain for such kind of priority queues. So let's furthermore down into the definition of a heap. So a heap is a binary tree. Where each node has an element. And for every node I, so basically we want to, because this is like a priority queue, we want to have some sort of way that we can express the fact that smaller keys represents higher priorities. So basically for this here, sure that for every node I, the element V at I and the element W at I's parent satisfies the key of W is smaller than the key of V. So basically, we want to make sure that the value in parent is always smaller or equal to the children. So I guess we are talking about binary tree, so we can definitely draw an example like this. So for instance, assume that this is like a 1 here. And maybe let's draw something here. So because here we are talking about the case where the parents are smaller than the children. So the value that we draw here, as long as it is a key, it should be larger than 1. So maybe let's, for instance, draw like a 2 here. So, sorry. So here, so there's, you see like in this definition of heap, there is really not like a difference between the left child or the right child. I mean, this is called the left child and this is called the right child. So there is not a significant difference, I mean, in the definition of the heap, and we are not actually going to worry about that. But as long as the parent is smaller than the children, we are good. So maybe let's, for instance, write something random here down. So maybe let's write 5 here. So we can continue. I mean, here for this 2 here, we can correspond. It can also has children. So for 2 here, maybe let's say like we can have 10 here. Maybe we can have 3 here. And maybe for instance, for the 5 here, let's say we have 7 here, and let's we have like 11 here. So you see that in this structure of heap, we don't have strong requirement about like, for instance, like the relationship between left child and right child. So for instance, like here, 10 is larger than 3, and actually 7 is smaller than 11. So we are actually not bothering by this too much. We just in general want to have a heap that the parent is smaller than child. I mean, there are more like intricate data structure that can have further restrictions on like the relationship between, I mean, children and in general different levels. But here in the heap, we don't require this. In general, we are quite relaxed on this. So let's continue. So that's, for instance, this is like a 15, for instance, and maybe, for instance, here is like a 17, and here maybe is whatever, like a 20, and here maybe, for instance, it's like a 9 here. And maybe, for instance, here we have a 15, and here maybe we have like an 8. So we don't always have to have like a complete binary tree. I mean, we don't have, for instance, like the first layer has 1 vertex, second 2, a third 8, and like there are like 16 leaves here. Sorry, eight leaves here. So we don't have to have a complete binary tree, but maybe we can consider like a case, maybe we have like a 16 here. Yeah, there is only 1 child. Maybe you can add another one later. So crucial, let's emphasize this again. Crucial is that each node's key is at least as large as its parents. Sorry. Its parents' key. So I think another very natural question is that here, okay, you see that I'm drawing like a complete sorry, not complete. I'm here drawing a binary tree here, so this is a very easy to look. But in general, for instance, imagine that you have like a computer. So how you would like to store such kind of heap? So how to store a heap? So you can consider something like this. You can consider by an array H, where the first element of the array is the root. And for any node I, the children of I are at positions. Left child of I equals to 2I, and the right child of I equals to 2I plus 1. And parent of I equals to I over 2. So let's give a specific example of how we are going to store a heap in the next case.